You tap Send. A photo leaves your phone, crosses a city, reaches the coast, dives into the ocean, and arrives on another continent before you can blink. Most people imagine that journey going upward, toward a satellite, but the most important part usually goes down. Far below waves, storms, and shipping lanes, pulses of light race through strands of glass no thicker than a human hair. Together, submarine telecommunications cables carry more than 99% of international data traffic, video calls, financial trades, cloud backups, government messages. The modern world is threaded through the ocean floor. The network is enormous. It is also surprisingly physical. It depends on factories, coastal stations, specialized ships, international permits, and crews that sometimes have to pull a broken cable from kilometers beneath the surface. This is the infrastructure hidden beneath the word cloud. And several times every week, somewhere in the world, part of it breaks. Open a map of submarine cables, and the oceans suddenly look like a global circulatory system. Bright routes connect North America to Europe, South America to Africa, Europe to Asia, and islands to the nearest continental network. The paths converge at landing stations, secure coastal facilities where an undersea cable becomes a terrestrial one. According to the International Telecommunication Union, more than 500 operational cable systems span roughly 1.4 million kilometers. Telegeography's 2026 map includes active and planned projects showing nearly 700 systems and almost 1,900 landing points. But the lines are not distributed evenly. Geography pushes cables toward practical routes. They need suitable beaches, stable seabeds, access to electricity, nearby data networks, and permission from every jurisdiction they cross. A narrow corridor can therefore carry an outsized share of regional traffic. That concentration creates efficiency. It also creates dependence. The internet feels decentralized because information can take many routes. But the physical network beneath it still has coastlines, bottlenecks, owners, and places where a single ship can see several cables passing through the same waters. Satellites are essential. They connect aircraft, ships, remote communities, and places where laying fiber is impractical. New low Earth orbit systems have also reduced satellite delay dramatically. But for the enormous, continuous flow of data between continents, fiber-optic cables remain extraordinarily difficult to beat. Inside the cable, information becomes light. Lasers flash through extremely pure glass. Different wavelengths can travel through the same fiber at the same time, each carrying its own stream of data. Engineers can increase capacity by improving the equipment at both ends, even when the glass beneath the ocean has not moved. The route is also comparatively direct. A signal does not need to climb into space and return to Earth. It travels through a controlled medium at enormous speed with low delay and vast capacity. That is why an ordinary video call can depend on one of the most ambitious machines humans have ever placed underwater. A transoceanic cable begins long before a ship leaves port. Engineers survey the proposed route. They study water depth, slopes, sediment, earthquake zones, fishing activity, shipping lanes, and existing infrastructure. Near the coast, the cable may need to avoid anchors, reefs, pipelines, and environmentally sensitive areas. Then the cable is manufactured in enormous continuous sections. At its center are the optical fibers. Around them are layers designed to carry electrical power, block water, resist pressure, and survive the environment. In deep water, where human activity is limited, the cable can be surprisingly slender. Near shore, it receives additional steel armor. The finished cable is coiled into huge circular tanks inside a cable-laying ship. Loading can take weeks. Every meter must leave the tank in the correct order, because the ship may be carrying a route thousands of kilometers long. At sea, the vessel follows the surveyed path, while equipment controls tension and pays the cable out behind it. In deep water, the cable normally settles onto the seabed. Closer to land, where fishing gear and anchors are a greater danger, a sea plow or remotely operated vehicle can cut a trench and bury it beneath the sediment. The result is a road for light, constructed across terrain that no passenger will ever see. From the outside, a deep-sea cable can look almost disappointing. It is not a giant tunnel. It may be closer in diameter to a garden hose than to the massive pipelines people imagine. But its layers perform very different jobs. The optical fibers carry the information. A conductive layer supplies power to repeaters placed along the route. Steel and protective materials give the cable strength. Insulation and waterproofing keep seawater away from components that must operate for decades. The repeaters are crucial. Even light weakens over long distances. At intervals along the cable, repeaters amplify the optical signal so it can continue across an ocean. They are sealed inside pressure-resistant housings and designed for extraordinary reliability. Replacing one can require a ship, specialized equipment, favorable weather, and days at sea. All of this engineering exists so that the cable disappears from daily life. When it works, nobody notices the glass, the voltage, or the machines on the seabed. They notice only that a page loads. The most common danger is not a spy submarine or a sea monster. It is ordinary human activity. Fishing equipment can catch a cable. A ship can drop or drag an anchor across one. Near shore, construction and dredging add risk. In deeper water, earthquakes and underwater landslides can damage several routes at once. Cables also age. Components can fail. Harsh geography can make a vulnerable route difficult to avoid. The International Telecommunication Union reported more than 170 cable repairs worldwide in 2025, almost 4 every week. Most failures do not switch off the entire internet. Networks are designed with redundancy. Traffic can be rerouted through other cables, data centers, and landing points. A user may experience slower service or no visible interruption at all. But redundancy is not equally available everywhere. An island connected by only a few cables has fewer alternatives. A country whose routes converge in one coastal area may be exposed to a regional event. And when several cables share the same geographic corridor, one earthquake or anchoring incident can create a much larger disruption. The network survives not because cables never break, but because engineers expect them to. When a fault appears, operators first measure it from land. By analyzing how signals return through the fiber, they can estimate the distance to the break. Network data, ship tracking, and environmental information help narrow the search. Then, a repair ship travels to the area. In shallow water, divers or remotely operated vehicles may inspect the cable. In deep water, the crew can lower a grapnel toward the seabed and carefully recover one end. The cable is brought onto the ship, tested, cut back to a healthy section, and sealed. The crew then retrieves the other end. A replacement length is spliced between them. Each optical fiber must be aligned with extreme precision. The repaired section is tested aboard the ship before being lowered back into the sea. The engineering can be delicate. The logistics can be worse. Weather may prevent operations. A repair ship may be thousands of kilometers away. Permits can be required from several authorities. Other cables may cross the damaged route. This is one reason the industry maintains specialized vessels in strategic regions. They are the emergency crews of the global internet. For much of their history, international cables were financed by groups of telecommunications companies. Sharing the enormous cost also shared the capacity and risk. That model still exists, but the balance has changed. Companies that operate global cloud platforms, search engines, social networks, and streaming services now generate and move extraordinary volumes of data. Many have invested directly in submarine systems that connect their data centers across continents. The change makes economic sense. Owning capacity gives a company more control over cost, performance, and future expansion. It also reveals what the cloud really is. It is not one invisible place. It is a chain of private data centers, public networks, landing stations, terrestrial fiber, and shared ocean routes. A message may cross infrastructure owned by several organizations before it reaches its destination. The architecture of the Internet is therefore also a map of commercial strategy and political geography. Return to the photo from the beginning. To the person sending it, the process felt weightless. The screen displayed a small animation, and the message appeared somewhere else. But beneath that simple action was a physical system. A local network carried the data to a larger one. A coastal landing station sent it into a glass fiber. Repeaters kept the light alive across the seabed. A second landing station brought it ashore. Data centers and terrestrial cables guided it toward the recipient. Ships laid the route. Engineers monitor it. Repair crews wait for the moment it fails. Governments approve where it lands. Companies decide where the next line should go. The Internet feels magical because this machinery has become dependable enough to disappear. But it has never stopped being machinery. The cloud is not floating above us. Much of it is lying quietly beneath the sea.